Hello everyone, it's Dr. C. Thanks for a great first lecture. We didn't get a lot of chemistry done today, but we did get a good start on the semester. So let's just continue where we left off. We looked at this energy diagram for a reaction. Reactants here on the left of reaction progress, products on the right, and we talked about where delta H was the enthalpy change, the heat flow for the reaction, and also something called activation energy. And we'll do more with activation energy a little bit later in the course. But again, make sure you know what we mean by enthalpy change. Make sure you know what we mean by endothermic, exothermic, and whatnot. Okay, system surroundings. That's going to be an important piece of figuring out spontaneity. The next slide I have here in our notes, we've already done this. Make sure you know how to use delta H of formation values to solve for the enthalpy change for a reaction, the delta H for a reaction. All right, we've done that. All right, so the focus of this chapter and also this short pre-lecture is this concept of spontaneity. What do we mean by spontaneous? All right, and the typical definition, which you need to know, is we're typically looking at reactions, and what we see here is a reaction. It is the rusting of iron, okay, the rusting of steel, which is mostly iron, of this car. A reaction once started, and we talked about this key concept in class. Some reactions you don't have to start. There's just, it doesn't require any energy to get it started, or there's enough energy in the surroundings to get it started without adding some more. But most reactions we have to get started. Think combustion reactions. Okay, combustion reactions are spontaneous, but we typically have to ignite them in some way. So a reaction once started continues without outside intervention. Another way to say that more simply is it just continues on its own. Okay. And combustion reactions, think about the combustion of gasoline. You know, we drop a match into that can of gasoline and we know it's going to continue to burn on its own as long as there's reactants left, as long as there's gasoline left, as long as there's oxygen left. That reaction will continue on its own. That's what we mean by spontaneous. Okay, so know the definition. The other thing to know is if a reaction is spontaneous in one direction, it's not spontaneous the other. So note this, you know, this beautiful car on the left, over time, if we leave it out in the elements, for iron to rust, we need water, we need oxygen. Things speed up the reaction too, like salt and other things. But that car over time will spontaneously rust. It won't go back the other way. Okay, so we'll typically talk about, something saying spontaneous in the forward direction, okay, which for us will typically mean, and that says direction, I'm sorry, which will mean reactant to product will be our forward direction. So if it's spontaneous in the forward direction, reactants to products, it's not spontaneous in the reverse direction, which would be products going back to reactants. All right, now we haven't really considered the reverse direction of a reaction so far in this course, but we're going to get to that and talk about reversible reactions where we have reactants going to products and products going back to reactants. But generally, spontaneous in the forward direction, it's not spontaneous in the reverse. Conversely, if it's not spontaneous in the forward direction, it is spontaneous in the reverse direction. All right, so I hope that makes sense. All right, let's continue with a few more notes. Again, these notes are posted in Sapling and also in Blackboard. All right, so this is kind of another key concept. You're familiar with potential energy. All right, you're familiar with potential energy. So in this case, this person is shown pulling up a heavy object on a pulley. When we get this object up to the top there, we would say that that object has quite a bit of potential energy. Okay, and if we let go of that rope, certainly going to be spontaneous that heavy weight will drop. Okay, well, it's the same thing for chemical reactions or chemical processes. There's also a chemical potential energy. All right, and it's going to go from higher chemical potential, just like here, high potential energy up top, lower potential energy down here. It's the same thing for reactions or chemical processes. Reactions will tend to go from a high chemical potential, okay, so salt by itself and water is higher chemical potential. Oops, I'm sorry. Oh, where did that go? Sorry. Well, I wrote off the screen here. So that higher chemical potential. And when that salt dissolves in water, okay, and again, the dissolving processes, and this is where I like you to think on a molecular level. That salt is composed of sodium ions and chloride ions. And we talked about this last semester. The water molecules surround that salt, that ionic solid, and the interactions between the water and the ions break that ionic bond. And we end up with separated ions in solution, positive and negative. Now, what's not shown here, and you should also think about, is each of those ions is surrounded by a number of water molecules. All right? And of course, this is not to scale. But this is a lower chemical potential. Okay? So just more like a mechanical system that we see on the left, chemical processes generally will go from spontaneous, from a higher chemical potential to a lower chemical potential. Okay, same idea. And another way to say that is lower chemical potential. Another way to say that is stability. We're going from less stable reactants to more stable products. So the products will be more stable, the reactants will be less stable. Okay? Some good things to think about in terms of, why are certain reactions spontaneous and others are not. Okay? We've already looked at this. Our focus is, do reactants spontaneously go to products or not? That's thermo. Next chapter, we're going to start looking at this energy barrier, this activation energy here that we talked about in class, and that will determine the speed of the reaction. So spontaneous does not mean fast. You can have spontaneous reactions that are actually quite slow. All right, and I think hopefully I have an example here for you next. Yeah, here is one that might surprise you. The conversion at room temperature and pressure, the conversion of diamond to graphite is spontaneous. Okay, so if we actually do the calculation, if we look at what's at a higher potential, chemical potential and a lower, this is a spontaneous process. It's just incredibly, incredibly slow. And the time frame I've heard for this process, so if you have if you have diamonds stashed away somewhere and you're worried about all your diamonds, the time frame for this reaction I've heard is about 1 million years. So don't worry, you'll be okay. Now, if we change conditions as an example, under much higher pressure, so deep under the earth, graphite spontaneously converts to diamonds. And that's, diamond mines and the whole bit, right? That under high pressure, we can force reactions to go other directions depending on the reaction. All right. Last thing I want to get you thinking about for today. There's really two pieces to spontaneity. There's the heat flow, delta H, the enthalpy change. But there's also something else, and it's called, and you've probably heard this term, it's called the entropy change. And that actually has the symbol delta S. Okay, entropy is another E word. We have energy, we have enthalpy, we have entropy. Obviously, E cannot go to all of them. So entropy is given the symbol S. Okay, Now, what does entropy have to do with? Energy is involved, but it's a little bit different. It actually really deals with what is called energy dispersal. Okay, so as just a quick thinking about spontaneity, reactions that lead to more dispersal of energy, and we're going to talk about what that is, tend to be spontaneous. So there's two things to think about in spontaneity. Heat flow, that's important, but the other thing is, does it lead to more dispersal of energy? Okay, so a favorable entropy change is going from, less dispersal of energy to the energy becoming more dispersed as the reaction runs. So let's do an example. The total energy of this system, we have two particles, each at 2 joules. Our total energy is 4 joules. Okay? Here's a different system where we have one particle at 1 joule of energy, the other particle at 3. The total energy of this system is also 4 joules. So they have the same total energy, but which one has more entropy and which is the energy more dispersed? And it would be this one. Okay, the two particles, the energy of that system is more dispersed. They're not at the same energy as opposed to that first system. So that's a very simple example. And the last thing for this pre-lecture, just to try to get this concept of entropy, this dispersal of energy. Oh, let me add to this one. Again, the reason why it's also, and I kind of jumped ahead of myself here, I was thinking of my next example, we could switch the energy. So these are two energy states available for those particles. We could switch those. So there's another way. We could have the blue particle up at 3 joules and the red particle at 1 joule. And it's another way to get to this 4 joules. So again, that would be another thing that tells us that energy is dispersed. There's only one what is called microstate here. There's only one way to get at that energy of 4 joules, where in this system, we can reverse the energies of those particles and get to that same total energy. So this second system, we would say, has 2 microstates. It has a second microstate where we switch those energies. So this concept of a microstate of energy, the more microstates you have, more energy dispersal, which is called a greater entropy. Okay? And reactions that lead to greater entropy tend to be spontaneous. Now there's two pieces though. There's heat flow, enthalpy, and also this entropy term. And we're going to have to put those together, okay, into one thing, one equation. All right? But those are the two key things that we have to look at. Things is not the best word to use there, but my brain's not functioning quite right at the moment. But two things are going to play into spontaneous reaction. We're going to stop here for this pre-lecture. Delta H, heat flow, but then how dispersed is that energy? And we'll talk more in class on Thursday about this concept of a microstate. The more microstates of energy, the more dispersed the energy is, hence a greater entropy. All right, let's leave it there. That's probably close to 15 minutes, 14 or 15 minutes. And we will pick up with this in class on Tuesday. See you then.